Hello everyone, welcome to Study EETech. In the previous video, we have seen three-phase rectifier using diode. Here in the part 2, we will take three-phase rectifier using thyristor. Three-phase rectifiers are of two types. One is called the full converter and another is called the half converter. The difference between these two is clearly visible from the diagram. There are 6 number of thyristors and there are 3 thyristors and 3 diodes. Also one freewheeling diode is connected. The load is taken to be continuous ripple free and we are considering here RLE load. First we will take full converter, then we will take half converter. In the full converter, this element is T1, this element is T2, this is T3, this is T4, this is T5 and this is T6. And the input voltages are three-phase balanced voltage A, B and C. How to draw three-phase voltage quickly and correctly I have shown in one of my video. You can watch that by clicking in the I button here. This point, this point, this point and this point, subsequently this point also, they are called the upper crossover point and they are called the lower crossover point. And these crossover points decide which thyristors will be forward biased. As we can see here, the upper thyristors T1, T3, T5, they are connected in common cathode configuration and the lower thyristors T2, T4 and T6 they are connected in common anode configuration. And in the previous video we have seen in case of common cathode configuration that thyristor will be forward biased which is having the highest potential at its anode, and subsequently in case of common anode configuration that thyristor or the diode will be forward biased which is having the least potential at its cathode. The thyristors having 0 degree firing angle is equivalent to the diodes. So we can say T1 will be forward biased here if the firing angle is 0. T1 is forward biased here because right before this point this voltage was highest which is nothing but phase C. Phase C means the T5. So right after this point we can see this voltage is the highest voltage from this point to this point, which is the phase A, and phase A upper element is T1. So T1 will be forward biased from this point to this point. Similarly T3 will be here, T5 will be here, and in the lower half from this point to this point this is the lowest potential which is nothing but the voltage B. Voltage B, the lower element is T6, so T6 will be forward biased here, and right after this point this voltage is going to be the least potential, that is VC. So the T2 in the lower half will be forward biased, so T2 will be forward biased from this point to this point and this will subsequently go on. So this is the 0 degree firing angle and the conduction times. T1 is conducting from this point to this point, T3 is from this point to this point. So we have drawn the conduction angles here, and the voltage that we will get I have shown in the previous video, which is nothing but the diode rectifier. Look at this point closely. This point's angle is 30 degree, right? Because till this point is 180 degree, so 3 equal segment will be 60 degree and half of that is 30 degree. So before 30 degree T1 is not forward biased, so T1 is becoming forward biased from this point only. So we will consider this is the 0 firing angle for T1. Though this point is 30 degree, but in terms of firing angle it is 0 firing angle for the thyristor. So we will take the crossover points as the respective reference point of the thyristors in terms of firing angle. So when we say the firing angle is 0 degree, meaning T1 is triggered here, T2 is triggered here, T3 is triggered here and so on. Okay, for 0 degree firing angle this is exactly equal to the diodes. So the voltage waveform we have already discussed in the previous video. Now we will change the firing angle to be 60 degree. What does that mean? T1 will be triggered right after the 60 degree. So starting from this point, if this is 30 degree, so plus 60 degree will be the 90 degree, meaning this point. So T1 will be triggered here, meaning from this 0 crossing point you have to go for the 60 degree, there T1 will be triggered. Similarly T2 will be triggered not here, rather right after 60 degree, meaning at these 2 points. Similarly respective firing points will be shifted by 60 degree with respect to this diagram. So coming back to this waveform here, this is again three-phase voltages. T1 will be triggered here, T2 is not here but triggered here, T3 is triggered not here but here. Similarly, every thyristor's triggering point have been shifted by 60 degree. So we see the conduction angles here. The upper group is called the positive group and the lower group is called the negative group. So you can see here in this segment starting from here, T5 in the upper group and T6 in the lower group. If T5 conducts and T6 conducts, what the voltage we will get? T5 is conducting in the upper group, meaning we will get the voltage C here, right? And T6 is conducting, meaning we will get the B voltage here. So we will get CB voltage here. Look, the voltage is CB, right? Similarly, you can calculate T1 from the positive group and T6 from the lower group. So T1 means phase A voltage and T6 means B voltage. So we will get AB voltage here, right? So we get the AB voltage here. Similarly, you can just calculate if T1, T2 conducts, then what voltage we will get? T1 means the upper point is A and T2 means we get C voltage here. So we will get AC voltage here. So we get the AC voltage here. So just by looking at this conduction angle diagram, we can write what the voltage we will get at the output side. Now what will be the waveform for VCB or AB or AC? That you can see here. Here we get the CB voltage, right? So VC minus VB. So we can see here, this is our VA, right? This is VB, okay, and this is VC. So in this segment we get VCB, meaning VC minus VB. So we have to subtract VC to VB. So we can see here, this is the difference and the difference is coming down. So we will get 0 here. There is some difference and the difference is coming down. So we will get some voltage here like this. Similarly, you can calculate for AB also. This is A and this is B. So the difference is coming down to 0. So we will get 0 voltage here. Similarly, other voltages we will get in this way. And this voltage will be 1.5 times of VMP, the maximum of phase voltage, that you can see in the previous video I have mathematically explained. In this diagram, we are showing instead of drawing the phase voltages, we are drawing here the line voltages. How to draw the line voltages from corresponding phase voltages? In the part 1 we have discussed. Kindly watch that video, it will be better to understand. What you need to do is that you need to draw this diagram from the positive group and from the negative group, and now you find out the segment who is conducting, right, and what the voltage you will get, CB. Note it down, CB you will get. Then copy the voltage of CB from here, which looks like this. So VCB will be here. Here we are getting T1, T6, right, meaning we will get AB voltage. You can see here T1A, T6 means B. So I will get AB voltage in this segment. So what does AB look like? AB is like this. So it will be just copied and pasted here. So actually three-phase rectifiers looks very difficult at the first instance, but if we understand logically, there is no such difficulties. In power electronics, everything is all about the which switch is on and which switch is off. Then the whole thing will come down to a problem of circuit theory. Now in this slide I have shown the voltage waveforms for 90-degree firing angle, 150-degree firing angle also, just by extending the thyristors when it is fired and what is the conduction time, then just draw the line voltages. You can just pause the video and look at this diagram. The way I have explained for 60 degree or 0 degree, you can extend that knowledge to find out the voltage for 90 degree and 150 degree. And here we are calculating the average voltage. So the average voltage starting from this point to this point will be the one period. So just by calculating the maximum of line voltage and sin omega t, the line voltage, we will get to this 3 VML by pi cos alpha. In the previous video in details I have shown the calculation. Now we are taking half converter. So here we can see that thyristors are T1, T2, T3 and diodes are D1, D2 and D3. So the only difference will be the diodes do not require the triggering, but thyristors require triggering. Three-phase line voltages are shown here, and the respective triggering of the thyristors are shown here also. For 0 degree firing angle, 60 degree. In between these two, the 15 degree firing angle has also been taken, then 90 degree, then 120 degree. So the process is same, just by find out where the diodes are conducting, where the thyristors are conducting. Keep in mind one thing, that is the conduction of the diodes are constant here, they will not change. Only the thyristor triggering points will change. If it is 0 degree, it will be triggered here. And if it is 15 degree, with respect to this point, it will be shifted by 15 degree. T2 will be shifted by 15 degree, T3 will be shifted by 15 degree, and this is shown here. Then you can draw the output voltages. Next, we are taking the firing angle to be 60 degree. So starting from this point, calculate the 60 degree and come to this point. T1 is triggered here, T2 is triggered here, T3 is triggered here. So this is the conduction periods for positive group and the negative group. See here, in the negative groups, conduction are not changing, but in the positive group, the conduction times are changing because of the thyristor, and we are getting the output voltages as the line voltages. Then 90 degree, then 120 degree. One point to note down here, for the firing angle 60 degree, the output voltage touches the zero axis. The firing angle before 60 degree, the output voltage does not touch the zero axis. If the firing angle is more than 60 degree, the zero duration of the voltage is appearing. If the firing angle is more than 60 degree, the voltage in this segment we will get line voltage VCB, but VCB cannot be negative because the freewheeling diode is there. Zero voltage we will get at the output. And if the firing angle here for 120 degree, we will get the discontinuous conduction. Before the VCB occurs, there will be the E voltage and there will be the zero voltage when freewheeling diode conducts. And this is the average voltage for half converter. It can be calculated from this waveform. From this point to this point 1 voltage, and from this point to this point another voltage. From pi by 3 plus alpha to 2 pi by 3 we get V ml sin omega t, and from pi by 3 to 2 pi by 3 plus alpha we get V ml, I think it should be ml here, sin omega t d omega t, and this will come to be 3 Vml by 2 pi 1 plus cos alpha. So the key difference between the half converter and full converter is that in case of full converter we get 3 Vml by pi cos alpha, so it is only multiplied by cos alpha, meaning the average voltage can be positive or negative. So here you can see the average voltage can go in the negative direction also, but in case of half converter the average voltage is coming to be 1 plus cos alpha, which means the average voltage can never be the negative. And also if there is a freewheeling diode, so the voltage negative swings will never occur, and subsequently in mathematically also we are getting 1 plus cos alpha, meaning the average voltage can never be negative. So as because we can get positive and negative voltage in case of full converter, but with respect to that here we are getting only positive voltages, that is why it is called the half converter. So just by varying the alpha you can get only positive voltages, so this is half converter. But in case of full converter you get 3 Vml by pi cos alpha, meaning positive and negative, so this is full converter. So this is the key difference between half converter and the full converter. Study EETech is dedicated to all the electrical engineering students, and our motto is to make the Study EETech complete platform for the electrical engineering students. Subscribe to our channel, follow our Facebook page, and visit our website. The links are given in the description. Thank you for watching. See you in the next video.